Hi everyone, my name is Robin Oval. I'm a postdoc researcher at the University of Cambridge in the UK, and I will be presenting the results of the research done on the ACORN project on automating concrete construction, and more specifically on our path towards off-site automated fabrication of segmented concrete shells as building floors. Our industry has a massive impact on our environment. Indeed, around 50% of the UK's carbon emissions come from the construction industry, and cement production only is responsible for 7% of global greenhouse emissions. But we have a lot of potential in our building floors or slabs to actually reduce the embodied energy of our buildings. Indeed, they account for around 60% of our structural mass, and by moving from thick reinforced plate system that work mainly in bending towards thin shell that work mainly in compression, we can reduce the embodied carbon in our structures. Furthermore, moving towards the circular economy of construction, we should design our structures so that they can be not destroyed but disassembled and rebuilt and reused. But this is actually changing when our concrete structures are monolithic due to on-site concreting or grouting that makes them hard to reclaim for reuse. To fulfill these objectives, we propose a segmented funicular shell. So in this system, the concrete works mainly in compression, which allows us to reduce the thickness of the system and use less concrete. And the shell is actually segmented so that the different parts are produced off-site, fabricated in a factory, before being transported and assembled on-site. A key challenge for this system is actually the connection between the different elements. And here we are relying on a key connection that acts as an assembly guide during construction, and then later also serves as a shear lock that prevents sliding failure between the segments in the meaningful direction. And thanks to this connection that works only in compression, it is easy to deconstruct and reuse this system for circularity by just putting back the scaffold system. The approach of the ACORN project relies on an end-to-end holistic vision of a digital workflow that takes into account design, optimization, fabrication, and planning, informed by the construction process. So starting with off-site automated construction, including actuated reconfigurables and robotic concrete spraying, to produce the different shell segments that will be transported and assembled on-site as building floors, and then later, at the end of life of a building, these elements can be disassembled and reused and repurposed for new applications. From now on, I will be focusing mainly on the off-site fabrication process that we propose. The Formwork system is crucial when it comes to build concrete structures, and particularly shells. Shells are extremely efficient structures thanks to their double curvature, but they're also more challenging to build due to their geometrical complexity. Indeed, the material and labor that comes from a formwork can account for up to 3/4 of the cost, which also has an environmental impact. To reduce this, we rely on a mold that is reusable, reconfigurable, thanks to a set of pins that can move vertically thanks to actuators. We're actually relying on a modular system that comprises 4 modules of 1 square meters with 9 pins each that can be added up in order to form the base formwork. Then this system actually supports a flexible formwork that consists of a network of rods that are supporting a membrane system on which lies a curved polygonal timber frame that delimitates the casting area. Manually pouring concrete to produce these curved segments requires some good traveling skills and also necessitates to vibrate the concrete. However, because of the curvature of the formwork, it also risks the concrete to slide down the slope. Therefore, we're relying on a concrete spraying that provides self-compaction of the concrete on the flexible former, guided by a robot to control the process and the output and automate this fabrication process. To do so, we are using a robotic arm connected to a spray station that allows us to spray glass fiber reinforced concrete. These fibers bring this nominal tensile reinforcement in the structure and also a ductile behavior. To validate our research and the different fabrication processes, we've been continuously producing prototypes and demonstrators, and we are currently working on a mid-scale prototype of a full segmented shell consisting of 9 segments with a span of almost 2 meters. The main goal here was to validate the pin bed mold concept. Over the summer, we've been producing it, assembling it, and testing it. The next is the large-scale demonstrator of a project of a shell that's consisting of 13 segments for 6 meter span, where all the different fabrication processes and technologies will merge into that final demonstrator. I thank you for your attention for the presentation. I'm looking forward for questions and discussions, and I encourage you to stay tuned to see more of our research with publications and prototypes coming up soon.